So for our next speaker, I'm very excited to welcome Dr. Karmen Condic-Jurkic, who's the co-founder and executive director of the Open Molecular Software Foundation. She holds a PhD in computational chemistry, and her research was focused on studying protein function and dynamics using multi-scale modeling techniques. During her postdoc years, she developed a passion for open science and research infrastructure. She's particularly interested in building new resources and making research infrastructure more robust, sustainable, and accessible, and facilitating large-scale collaboration projects, which I'm sure she'll mention briefly in the presentation today. But let's have a round of applause to welcome Karmen.
Yes. Okay. Awesome. Thank you. Thanks, Johnny, for this nice introduction and also for the invitation to talk to you all about what we do at the Open Molecular Software Foundation. So as Johnny said, my name is Karmen Condic-Jurkic. My last name is somewhat unpronounceable because I'm originally from Croatia, but don't get intimidated. You don't have to call me by my last name. I'm the executive director at the Open Molecular Software Foundation, and the title sounds more glamorous than the job actually is, but I actually still really love my job. And I guess I would like to say to you why I really enjoy it. So OMSF is a small not-for-profit based in the US, and it's founded 2021 with the mission to actually improve research software in molecular sciences, open source research software. So the goal, one of the parts of our mission is to build good open source research software. And now why is that a goal? Because I'm sure, as probably many of you have experienced, research software is not always easy to use. And especially if it's open source, sometimes you need to spend days to make things work, or then things break and you have nobody to ask to help you or to fix it. So overall, there is like a term that I came to love, which is called abandonware, right? Like a lot of things get developed, but then they get abandoned. And, some things are useful, some are not, but, it's a problem. And then we also want to professionalize this research software development. A lot of research software is developed by people like you, by PhD students, by postdocs. Then, like during your PhD projects, you move on to your next role, to another institution, to another project. Things that you've built previously, again, become part of this bigger abandonware ecosystem. And again, it creates a problem. And similarly, building research software or like building software in academia is poorly aligned with like academic goals, right? Like you don't get rewarded, for writing really detailed documentation, for providing tutorials to your fellow students. It's just like you have to publish a paper, right? But these things are kind of like misaligned. And finally, like not everyone wants to be a PI at the end of the day, but like some people still enjoy, developing software, doing research, but not necessarily with the same career outcomes as what academia offers. So we are hoping to kind of offer roles such as research software engineer, documentation writers, project managers, hopefully one day UX designers. That's something we're still missing. But yeah, anyway, trying to create new roles and new jobs around research software development. We also want to provide useful content, like, again, good documentation, good tutorials that are also up to date. Hopefully, some other content like, benchmark reports or other kinds of reports that, our broader community finds useful. This is something I think that we have we are doing some work, but I think that there is a lot of space for improvement. We also want to facilitate collaboration and exchange of ideas and expertise. So we want to bring, people who want to, let's say some problems are common, right? Some infrastructure parts, like everyone is interested in certain tools. And so one thing that we want to do is kind of avoid duplication of efforts. So we don't want to have like 10 different solutions to the same problem, which we kind of see often in our field. And also, we want to bring also academics and industry people to talk about what are optimal solutions, because all these researchers kind of need to use these tools. And finally, we want to be sustainable, meaning that once we build something, we want these things we want this something to last for a while, right? We want it to be maintained. We want it to be up to date. We want, for example, new version of NumPy came out a few days ago. We want to make sure when that happens that the whole thing doesn't break, that people's workflows are still operating, so that, you know, that there is someone who can take care of things as world is changing. I was thinking like in my mind, like software is often like having a guidance, right? Like you can design a guidance that's easy to maintain, and maybe you just need to water it every now and again, but still some effort is needed if you want this guidance to look nice and tidy. And how we kind of see ourselves, we kind of want to be placed in this sweet spot between industry and academia, right? Like what we see in industry, for example, is that they have different problems, right? They need to, if you are working in drug discovery, if you talk to people working in industry, they are there in support of medicinal chemists. So they need to help medicinal chemists sift through, like, obviously these bazillions of potential compounds that are might or might not be drug candidates. And they have like limited time frames when they need to deliver the results to their fellow team members. And they don't have time really to spend 1 week or 2 weeks tinkering with tools and making things work. It's like, I have an hour and it either works or it doesn't work, right? Or also they have like firewalls. So meaning that updating software very often means that, you know, you might break their workflows very often, which is also not a good thing. Obviously, in academia, there is a lot of like new development, methods are progressing, and people are trying new things that might be more effective or are solving problems better. But because they are in this experimental or let's call it prototype stage, they are not in the state to be used like in the industry. And so we kind of want to bridge that gap and make sure that like new advances in academia are translated into stable and robust software in industry. I just also want to say, I forgot to mention, but if you have any questions or want to interrupt me at any point, you are very welcome to. We have an hour and it would be nice to have a conversation rather than if I just talk at you all the time. So how we see at the moment, we are primarily funded by industry in the form of like consortia. So when we have a specific project with a specific goals, we form a consortium around it, where we have like big pharma companies and small biotech startups coming together and then fund these projects at different membership tiers. I'll get back to it later. And then we also collaborate with academics. So we have also PIs working on these tools. And so they all come together to discuss what the roadmap is and how it all should move together. And that model has been working reasonably well in the so far, at least. We are also applying for grants, and grants are in our perspective meant for things that, you know, for one-off deliverables or things that, you know, we can kind of do specific interventions, because again, for grant funding, it's not really sustainable, but it doesn't mean that you can't fix or help fix some problems that exist in the space. So we got CZI funding so far, we got POST funding, we got some NIH funding, and I think our like long-term sustainability plan is kind of bring like use both revenue sources as our sustainability model. That is like have industry funding, but also grants as something that pushes the whole organization forward. We can also accept donations, but I must admit that we haven't really relied on philanthropy so much. It requires like, I don't know, building relationships with rich people and, you know, stuff like that. And that takes time. And we had other things to do, but maybe in future, maybe we should look into that revenue as well, source revenue. One thing that these things are working really so well is that we are having like the same IP policy for everyone who joins OMSF projects. Essentially, everyone who joins agrees that whatever is being built will be released under permissive licenses, which is mostly MIT for code, and then CC0, CC BY for data. And that incredibly simplifies the thing. When you are trying to, I guess, negotiate with pharma industry, you have to talk with their lawyers. They're obviously very sensitive around anything IP related. So you don't really want to have like specific negotiations with every member of every industry partner that comes and wants to join your project. So this is kind of like building a nice neutral ground where we say, this is like where we all come to play in this pretty competitive effort. We want to build better tools for everyone. And then whatever we build, it will be like freely accessible to everyone, and they can take it and modify it. And it works well, you know, both for industry and academia. And because a lot of pharma companies have already agreed to these conditions, it's easier to sell it to others. For example, it's easier for Novartis to say to, you know, or, you know, our advocates to their manager, it's easier to say, oh, Bayer has signed it and AstraZeneca has already signed it. It makes them, you know, okay, you know, if others are doing this, so can we. So it kind of builds trust, which is really important for this space. And as I said, like consortia are then built around membership agreements. We have 3 different tiers, mostly at 150 and 20K per year. And depending on, like, not every project has the same agreement, but more or less when you join, you get access to the advisory board. And from the advisory board, you can elect people into a governing board. The governing board essentially provides the oversight over the whole project, approves finances, general roadmap, and some big decisions. But the advisory board provides also a lot of input in terms of like what are the desirable deliverables, what people want to do, what they want to build. And then OMSF hires more or less a core team of developers and maintainers and people whose job it is to actually build these open source tools for drug discovery. What we also found that works well if there is a lead team or a single just makes life a little bit easier when it comes to communicating, making decisions, and similar practical things. So a brief history, just like how we started. It all started with Open Forceville in 2018, which was the first project with the first consortium that was built in this way. And it took about a year and a half or so to kind of come up with the agreement to like go through all the legal reviews between all the legal teams of the founding companies that were present, and it was Bayer and Merck, and I don't know, there was like a 5 or 6 of the GSK participating in this process. It's a long process to actually go through legal review of things. Do not underestimate how agreements and law and legal process can block you sometimes, even when you are trying to do something fun and good, and that's what everyone wants. And at the time, Open Forceville was housed at Virginia Tech. But as the time was moving on, we really realized that it doesn't work. Like being a part of academic institution was just not really good for us. Their business is education, right? So like they are sometimes slow to respond, which for us meant like sometimes almost losing financial support because again, pharma operates at different schedules. If you don't take or pull money out fast enough, then the budget gets, you know, redirected to something else, like you didn't spend it. So there are like time pressures. So you kind of need a little bit faster operational support and something more responsive. We also realized that having research software engineers embedded in the research labs is also not necessarily the most productive way of developing software, and also it doesn't provide a growth path for these people. They forever, you know, remain embedded as someone under a PI. So like even if the whole thing moves forward, you are always like you can't really. There's a ceiling, right, as far you can go in this environment. And so, and then there was, as OpenFF was becoming more successful, there was kind of the interest started to grow for other projects to kind of function in the same way. And we realized that maybe we can try to spin up not for profit and see how it all goes, which we did in 2021. And then we spun out the next project, which was Open Free Energy, which is a project building infrastructure for free energy calculations, predicting binding free energy of small molecules to targets of interest. We then transferred Open Forceville from Virginia Tech to OMSF. We also then then in late 2021, AlphaFold came out. And then soon after, I was contacted by people, oh, you are doing this. Can we maybe build something similar so we can come up with the open version of AlphaFold? Because at the time, it wasn't clear that they will open source the entire thing. They open source the code, but the weights and I think training data was not available. So there was no possibility to retrain models internally, which was obviously of interest to pharma companies because they have a lot of internal data that they don't really share publicly. So they can fine-tune things. So that's how OpenFold was born. And then we got our 501c3 status and other project joins such as WESPA. And then we are now also hosting the Open Rosetta, which is the version of Rosetta Commons that are trying to Rosetta Commons is considering also to switch to open source model. And we are hosting all of their community building efforts and new things that are coming from that community. I would also like to highlight BPDMC, which is Boston Protein Design and Modeling Club. Similar to something what Valence Labs is doing here. They're hosting monthly meetings on various topics when it comes to protein design and modeling. So if you find yourself in Boston, go and have a beer or pizza with them. This is kind of how it is. And they record everything and post it online so you can also watch things there. So most of our projects are still physics-based, I guess, other than OpenFold and some things coming from Rosetta. But a model is a model, and some challenges and issues plague every model, whether it's AI or a physics-based model. There are always limitations to what you can do with them. So I kind of wanted to quickly summarize what is this roughly a life cycle of a model or a tool. First, obviously, you have to define what's the problem that you are trying to solve, which will inform what solutions you want to employ and how you want to develop it, et cetera, et cetera. And then you embark on development, and you obviously talked a lot about, I think in the past days, how to develop new AI models, what new technologies you can use, and so on and so forth. And then after that, I think the good thing is to kind of probably figure out how your model performs compared to others. Is it fast? Is it slow? Is it better than this thing or that thing? So that's also something you want to know. Then you release it. And now that depends again, maybe it will be an open source thing. Maybe you want to follow some commercial paths. Again, multiple choices there. And then finally, you also have to decide, is this something, that is going to last? Is this something that you want to maintain in the future or not really? And even if you do decide to maintain, do you want to offer some support to your users or also not, or just keep it alive? Or, there's a spectrum of answers. And obviously there are variances of this, but this is kind of, I think, a roughly good general model of how it all goes. And so I kind of want to go to the problems, go back to the problem statement. This is actually a really important part. And I think that sometimes is, not really thought enough about as it should be. There are interesting problems, and we sometimes fall into doing something without really stopping and saying, hey, why am I doing this? Who is this for? How long should I be doing this? Are there any specific conditions or terms that I need to worry about? Is this just for my PhD? Is this something bigger than that? Or it's just for me to have fun? Again, what is the problem? And all these other questions that come with it. And as I say, if you're just doing it for yourself, obviously it comes it doesn't really matter what you do. You don't have to worry about anything. It's just for you. Nobody will look at it, or so you don't have to worry about it. So you can do whatever you want, right? But if you decide that you are building not just for yourself, but for others, then there are things that you need to start thinking about. And the sooner you start thinking about it, the better it is. It just makes your life easier. And it's not always, easy to know where you are on this slider. Maybe you start something and you think, oh, this is just for fun, but then it becomes something, more then gains traction, or you think, oh, this is really great, I'm going to build this for everyone, it's going to solve everyone's problem, but then it just doesn't work out. That's all fine. But it's really good to kind of every now and again to take a stop and think about where you are on this slide. because if you want to engage with your users, if you plan to have contributors, again, the sooner you start thinking about it, the less work you'll have in the future. And one of the choices, I guess, that you have to make in this process is like a license. So do you want to be open source, or do you want to be a commercial license or closed, or do you not even ever want to release it, what you're doing, and, just keep it hidden? That's all, again, everything's fine, but you just have to decide what it is that you want, because it will affect how you manage your project going forward. And obviously, if you decide to go like fully open source and use permissive license, which is overall wonderful, like, I guess, for humanity and community, but it's like it's very difficult then to change your mind later and say, oh, I want to switch to commercial license. There's a question. So we are not using like there are obviously examples in the broader community, but we are not using it because industry is allergic to GPL licenses, and on and another thing is, like, I think our mission is really just to make it easy for people to reuse it. And while, the copyleft license has its, goals, values and stuff, I think our goal is just to facilitate innovation, right? Make it, it's not so important that we enforce that everyone else is doing contributes back to open source. You can argue like for one thing or another. My personal view, and this is like my very personal view, is like, if you are being funded by taxpayers, then it belongs under permissive license, because industry pays taxes. There are also users and like contributors to science that comes out from federally funded or whatever grants funded research. Privately funded thing, I think you have right to do whatever you want, and manage licenses again however you want. Now, this is my very personal opinion, so it's not something, it's not a recommendation. It's just like, that's how I see things. Yeah. What happens when there is a modern or incorrect practices? How is the accountability managed? I missed like a part of it. How is accountability managed when what happens? Can you please repeat?
Sorry, do you want to use it?
In cases of some like errors made by the system or something, like how is accountability for errors managed in that case?
Oh, I mean, well, for one, there is no software and there's no research without errors. That's like number one, right? And I think the existence of an entity is actually a way to deal with this accountability, right? Because, as I said, we are trying to professionalize the team so that when something does break down, you actually have an email address or a way of contacting someone who can fix it. And you can say, I have a problem, I found this error, or, something is breaking for me. And there is a person you can reach out. Because often, again, as we discussed before, if there is a PhD student, they moved on, they don't really do the thing, or it was left in the lab. Like there are like obviously different ways of dealing with these problems, but nobody's responsible. And to be fair, like you shouldn't offer support just because you did something, as a part of your PhD project. Doesn't mean that you have to be like bound to something for the rest of your life. So we are trying to find a way that when people finish their PhDs, if their thing that they have developed during their research or postdocs, if it gets integrated into the main code base, then it becomes responsibility of the core team developing, code for a specific project. So that's the idea. Yeah.
Any other questions? If you raise your hand, I'll just bring the microphone to you.
I think one over there.
So I just had a question about, so like when you release a tool or a model, how do you keep it like open source, but also like really encourage people to like give you credit if they use like your code or something?
I think, well, when your tool is really super useful, everyone will use it. Now, how to, and you will get recognition, right? Because people will recognize good work. Now, how well would that recognition translate into your opportunities to land an academic job? That's something else I mean, there are so many conversations, I guess, how to what metrics to use for research software development. Is it citations? Like, how do you, and I think, things are moving forward in that respect. I think it's much better now than it was like 5 years ago. There is more recognition for these things, but it's still, I don't think there is like one simple answer. And you just have to count that people will give you credit where credit is due, I think, which is kind of how we operated for many years now.
Gotcha, thank you.
So yeah, going back to licensing, it's, releasing things under permissive licenses, like, letting the genie out of the bottle. You really can't put it back in very easily. Like, you can change the license later on, but it's much easier to like release something under very restrictive and then, make it more open gradually. That's like much easier this way to go, but not vice versa. And as I said, like, to put it in geeky words, permissive is kind of, you're entering high entropy area, and restrictive is more like low entropy. And it's obviously, there is a directionality here embedded in this process. And something I kind of also wanted to, going back to the something along the line of the questions just asked, there are differences between copyright and license. And I think that oftentimes when there are these conversations in the academic environment, I think there is not really clear understanding of what it is. So copyright is a type of intellectual property, it says here, that protects original works of authorship. As soon as an author, I have to remove this, I'm sorry, fixes the work in a tangible form of expression. So if we just have a conversation, that's not a tangible form of expression. So it has to be written down somewhere or recorded in some way or published on GitHub or something like that. But then you attach a license to that, whatever material you created, right? Which is the way of giving, like, you give your user some rights on how they can interact with this material that they have created. You still hold the copyright, but if you say like, unless you release it under CC0, then you kind of relinquish your copyright and it just becomes a public domain thing. But if you use, for example, CC BY, you still hold the copyright. You can even change it later on, and you have rights as the author here. But so it's not the same thing. You still have, as a copyright owner, which is sometimes what you do, like you transfer copyright ownership to publishers when you publish some papers with traditional publishers in academia. You are no longer a copyright owner, for example, in that case. And obviously similar goes for like software and data licenses. And another thing that that didn't quite work, but I also wanted to say that if you use, for example, CC-BY, which means by attribution, attribution means something necessarily, right? So it says here that you have to satisfy, it's a license condition, like it's a legal requirement of that license conditions, where actually citing someone's work when you are publishing a paper is a norm, right, in our community. So there are differences there. Someone can like satisfy legal requirements of the license, but might still not cite your work in their paper, and that's sometimes what counts, for your career progression, if that's the path you want to take. And now there's a lot of discussion. What are the licenses for AI models? Because it's both. Actually, there's like so many conversations around it. You can go to the, for example, open source initiative to look at like what the conversations they're leading about it. Like it's not just, like what are the terms and conditions for to use, the code and data associated with it, but it's like how to use AI model in totality and what it means. And even like what it means to have like an open source AI model in this. I can't summarize it for you because it's just like it's an ongoing conversation, similar to like biosecurity and ethics, etc. So I think this is something to keep an eye on, and I think we might summarize it in a year or 2 or 5. But now it's just like lots of opinions, I think. But if you want to learn more about licenses and how to even manage open source projects or manage collaborations, I would highly recommend the Turing Way. There's a link here, you can go there, and then they have like all these sorts of guidebooks and guidelines on how to do it, like explanations how licenses work. So you can really learn a lot there. You can also go to obviously all these places like Creative Commons. They have, for example, CC license choosers, which is like a little tool that can help you pick the right license for what you're trying to do. Similarly, Open Source Initiative lists all currently OC approved open source license, and there are new initiatives like the Rail initiative again around creating new AI licenses for AI models, which are conquering the world. And so I'm not going to talk about model development, which is the next thing in that life cycle thing, because you have discussed it for days, but I will talk a little bit about performance and why is it important. I think the key ingredient, so once you build a model, you want to communicate how well your model performs and where it performs well, right? So people know when to use your model or whatever it is, or your tool, more broadly speaking. And then to do that effectively, you need to choose the right metrics, right? Again, going back to what is the problem that you are trying to solve, and then also what are the good metrics to describe performance there. And when it comes to research software, like the most important metrics are actually those describing how well does this tool solve the research problem. And once you know that the tool is solving the research problem well, then you can worry about whether it's fast, you know, how you can optimize it, you know, for this architecture or this cloud deployment or that. That's all irrelevant unless your tool does what it's supposed to do, right? You can have the fastest tool, but if it gives you the wrong answer, it's not really good enough. One of the really good papers is called Pose Busters, which is that came that's kind of like looking into performance of different AI models predicting binding poses in proteins. I'll talk about it in a minute in more detail. But yeah, the second thing is that you want to think about is like, you have to know the limitations of your training and benchmarking data, right? Like saying, oh my God, we have like our models predicting great, like our variances and our MSCs are so small, but you know, if your data is messy, it means nothing, right? You are just fitting very well to noisy stuff. And I think one of the best places to kind of read about data sets and challenges in drug discovery is this Practical Cheminformatics blog by Pat Walters from Relay Therapeutics. So if you don't know about this blog, I highly recommend it. He really puts some very valuable content from someone who has like hands-on experience in drug discovery and has spent years like developing and using computational tools. And finally, you need to be honest, right? Because if you're not, people will come with great expectations and you will ultimately disappoint them. So in the long run, the best strategy is to say, hey, my model is working really well in this space, but is really bad in that area. So this is where you can get good results, but do not, you know, abuse our model and try to, you know, apply it for problem spaces where it just doesn't perform that well or it's not even meant to. And I've been reading lately the Confessions of an Advertising Man by David Ogilvy, and it's surprisingly how many of the lessons that he come like from advertising in 50s and 60s can be applied still on research and how we communicate, you know, benchmarking and various results. So he says, I always tell prospective clients about the chinks in the armor. I have noticed that when an antique dealer draws my attention to flaws in a piece of furniture, he wins my confidence. The same way, like if you are open and honest about, again, where your model or tool is not working, you get people's trust. Then they trust you, right? And they'll be like, okay, we know that if they say this, then, you know, we can go on and just do the thing. We don't have to spend days and hours like testing and trying. And that's incredibly valuable to everyone, right? Like, so that you don't have to spend your time doing checking and, you know, another round of benchmarking, even though every now and again you will have to. And then he also has like the whole list of like how to sell drugs, medicines, right? And one of the things is also do not strain credulity. A person in pain wants to believe that you can help him. And if we think about that, you know, let's say industry researchers or other researchers have problem that they want to solve using your tool. Again, if you overpromise and under-deliver, they will be disappointed, and ultimately you will lose their attention. And going back to the Postbusters paper, what they are discussing in there is the usual metric used for, like, shall we say, is assessing the goodness of binding poses of small molecules in proteins, right? And that's RMSD. RMSD is a good measure for something, but not, I see it as a nice, cozy, fuzzy rug under which you can sweep a lot of problems with things if you are not very careful. But, you know, you can say, oh, it's doing really well. It has like RMSD under 2 angstroms. And so they have developed all these other metrics which kind of look into chemical validity and consistency, intramolecular validity, which is more or less a list of like molecular geometry and energetics assessments. Intermolecular validity are things clashing with the protein and other surrounding molecules and similar things. And so when you look here, these are like the classical docking softwares, and they're doing really well. Let me explain. So these are like green and orange are different benchmarking sets. The full bars represent results that came from RMSD and Postbuster metrics, like, so the things, how well they perform. And then the stripy bars are just for RMSDs. And so we can see that all these tools, the AI tools are doing pretty well when we just look at RMSDs, but when we kind of dig deeper, then, you know, there are problems. There are problems with molecules. And some of the problems, for example, is like in here, double bond stereochemistry not preserved, bond lengths too long, bond angles too extreme, internal clashes, aromatic rings puckered, double bond not flat, energy ratio too high, etc., etc. Some of these things you can fix by relaxing your prediction by running, I don't know, molecular dynamic simulation or just like relaxation. But some of them you can't, right? And at scale, you have to, it becomes also expensive, and you might not want to do that for like a lot of structures and gases. And I think I personally also have a huge grudge against RMSD. I spent a lot of time during my postdoc trying to like figure out how to represent what I'm seeing in my simulations and how to quantify it, because RMSD also for like generally conformations, like when you want to judge like conformational changes in proteins and stuff, it's good, for example, for translational movements, but it's not really good when your like secondary structure changes, because these changes are subtle and the RMSD is not really high. But so you don't see it, you don't capture it with this matrix, right? So what I saw, for example, when I was simulating this transmembrane protein, is that my transmembrane helices were unfolding, but RMSD wasn't, like, it looked, you know, finish, so to say. And there were like 3 different crystal structures with different resolution, prepared in different conditions, and they were unfolding at different rates. So I didn't know, is like, are the crystal structures problematic? Are my simulations problematic? Are my force fields problematic? What is the problem? Why is this protein unfolding? Is that like a conformational change, or this is just like the system breaking down because it's so unhappy, right? And what you kind of want to look at in this case is like your secondary structure content, right? So you want to measure that. You don't really want to measure RMSD. But sometimes, and this is like the challenge with research, you don't know what is the metric. You don't know what is the thing that you want to measure, and you don't know how to define it. But going back to like OMSF and our projects, so what benchmarks are really important for us. They're important also for industry people because they need to know, again, what works well, and they have to like know it in a reasonable or like very short time frame. So they love benchmarks and they want more of it. And so so the whole open force field initiative has kind of started to work on like how can we actually even assess force fields, for example, how force fields perform compared to other either like publicly available force fields or commercial ones. And now I think there is a process more or less, or like a set of metrics that is being done routinely, or like that new releases are benchmarked against routinely. So you benchmark geometries, like force field optimized geometries versus QM geometries. And again, of course, you look at RMSDs, it's still very helpful. This is just for small molecules, but they also use this torsional fingerprint deviation, which kind of looks like how, let's say, looks more like from internally how your molecules and conformers differ, right? From MM optimized versus QM optimized geometries. And then you can compare it for like all sorts of different force fields. These are like, you compare it with GAF, which is another publicly available force field, and OPLS, which is a commercial and probably state of the art at the moment. But the difference between OpenFF is that OpenFF has maybe 200 parameters, and this OPLS has, I don't know, probably 1,000. So it's order of magnitude more parameters because you kind of fix issues by adding more parameters. And also you check the energies, and you can read the paper about what's being done here in this article. And one of the nice things that came out from in this benchmarking round is that now that everyone knows what values need to be measured and how all these things are computed, then the industry partners could just go and compute it even on their own proprietary data sets and then report back to us how it performs. So we don't need to know what molecules they have used in their calculations, but we can know like, what are the average RMSDs? What are these TFDs and energetics differences? We can know if the force field works well on these data sets, even though if we don't know exactly what is in the data sets. And then another effort that came out from OMSF projects, which is both OpenFF and OpenFE, are best practices for constructing, preparing, and evaluating protein ligand binding affinities. I mean, that's ultimately what pharma wants. They want more accurate force fields so they can predict more accurately what are the binding affinities for small molecules to their targets. But when you try to like run these calculations, there are so many recipes out there, like how to do it and which data sets to use. And so this was an effort to, again, it brings people from industry and from academia to sit down and discuss what these best practices are. And these include like, how do you select your data sets, both structural data to run your simulations, and then experimental binding affinities against which you compare your computational results. How to set up these calculations, and then how to run because there are many ways of how people analyze and then present data sets. And then finally, what are some learnings and recommendations, like, from obviously a lot of, trial and error that has experience, let's put it in a more of favorable way of what people learn by doing these calculations. So, for example, this is just like a list of things that you can think about. So what are the recommendations? Like select the best available structure, because sometimes there are multiple structures in PDB for the same target, and some of them are better and some of them are worse. You can again, there are like some recommendations of what you should look at in terms of like quality of resolution and electron densities. Because it is tricky, right? And I mean, whoever has ever looked at PDB files, and especially those like with ligand bound, ligands are often determined at like lower resolution than the protein. So whatever you have in the model might not be very accurate. And now we have all these AI models of training on PDB data because that's the only thing that's publicly available, but not all crystal structures are the same in there, like they don't have the same quality. And obviously things get even worse and more complicated when you have small molecules floating around it. And to prepare these protein ligand structures for binding free energy calculations, there's like a lot of cleanup involved in the process. You have to look and remove some things, you have to add some stuff, you have to check for protonation states, especially if they are around the ligand. You have to make sure that all that works. And then people do it in different ways. So you can give the same input file, PDB input file, and you can end up with vastly different results because people will make different decisions in this preparation process. And finally, even when people present results, they choose different ways. So the paper suggests also how the results should be presented. And this is like this panel A describes. So you keep, so everyone like can just determine on a glance like how the benchmarking is performing. So you are not trying to like make your data look better just by skewing the axis or doing some other tricks of that kind, because it happens quite a bit. And these benchmarking studies are extremely painful. So I don't want to make them sound glamorous. They are so important, but they are just like really tedious, slow, unrewarding work that is difficult to get funded, but everyone would like to know how things work, right? Like if you're a student or if you are a postdoc, this is the work that, probably won't get you promoted because it's not novel, right? Like you are not doing anything really exciting other than, people want to know what the result is and might get, cited a fair bit, but it's not considered novel research, right? But, because that's not our goal, we can make it our mandate to actually, push for these better benchmarking studies or think about them more, or even like, and try to like rally people behind it. And what is really kind of like what we are seeing now is that we can if we provide a protocol to our industry partners, they will go and run it and they will come back and report this, which is incredibly valuable. And I think we are just starting to understand just how valuable these things are. So much so that we have now people approaching us and asking, because Open Free Energy Project will start running a new benchmarking studies, that we have non-member companies asking, hey, can we join and participate in your benchmarking studies? That's really cool. Another difficult thing is data set curation, and even come up with a data set, things change, and it's an ongoing process. Going back to the whole garden metaphor, you just have to keep weeding and maintaining your garden, including data sets. So as I said, it's really hard work, but it's necessary and someone has to do it. So I just like before I came to give this talk, I just like sent a quick survey to my team and asked, so do you think that your tools or models developed in your project are appropriately benchmarked? And like 30% said yes. And then we have what, 1, 2, 3, 4, 5, 66 shades of no, I guess, in different ways. Like could be improved, could be better, sort of, we're working on it, some things are good. Like, well, it's kind of a no, right? And I think this is my favorite quote. We exceed community standards for benchmarking because there are almost none, though we should still be doing more, so the bar is really low at the moment. And another problem that we are facing is that there are not so many high quality publicly available data sets. They're all scraped from literature, and then you don't know where they come from or what conditions they were collected on, or you have too many data points in this space but not enough in some other area. And so it's really tricky, especially again if you don't have money to kind of commission experiments that can help you your projects. And so these are all complaints that kind of our team has listed, and there's like data quality and limited scope, shifting standards, lack of implementations of standards, and unresponsive maintainers. Like, for example, PDB should be a standard, but there is not every, but so many different software packages in molecular dynamics world has their own definition of the PDB file. That's not really a standard if everyone kind of takes their own view of what that file means. Slow and unreliable access, limited size of data sets, or something that's useful enough, understanding the suitability of given data sets for my needs, or like what went into the data sets, e.g., is it a conglomerate of many different assays, experience with wildly varying procedure, or is it something clean or performed at one place by one person on one instrument? And this is like, I like this, what would help is like having nutrition facts or like better documentation for data sets. And better way for discovering. And again, more complaints, I guess I'll skip it, but to summarize it, the issues are both with quality and quantity and accessibility, like where do you find it? Can you, even if you find it, can you download it? Can you even use it? And even if you use it, like, do you know what's inside? Is it consistent where this information is coming from? Is it reliable? Who is taking care of it? Is it going to disappear? Do you have to just run quickly and grab it and download it now before it just goes somewhere in the abyss of internet's wastelands? For metadata, so you don't know what's inside, you don't know the instruments, like you just don't know anything about how data was collected, especially, and I think that's often the case for data sets that are kind of that are generated by browsing literature and just pulling the numbers out of papers, because papers often just don't describe methods at sufficient detail. And then finally, there's like format standardization and adherence to it. You can even define a format, but are people going to stick to it is another question. And all of that makes, I think, life very difficult for everyone who wants to develop AI things and needs a lot of data in there. And I think a very nice paper is also about this problem. It comes from Greg Landrum, who is the IDKit developer, and Sarina Riniker, and they are looking into like how combining IC50 and Kaya values from different sources is a source. So you're better off overall to kind of use a smaller set than actually making your data set bigger by tossing all these different sources together. If you would like to, share your opinion, how you feel about benchmarks and data, I left the QR code. I would appreciate I'm kind of trying to figure out how people feel, and more than anything, I'm trying to like figure out, are there any good sources or resources that I'm not aware of? Because that would be really nice to know. And then, what are the solutions to these problems, and how can we actually get these nice public data sets? I think whatever we decide to do is going to be expensive. It's going to take a lot of time and money. So I don't think that there is an easy solution, but it would be great to have new clean data sets that are easily accessible with rich metadata schemas. So you actually really know what's in there. There are specialized repositories, so actually you know where to go. There are a lot of like general repositories like Zenodo, for example, and you go there and you can't find anything. People do upload stuff and share it. It's just that you can't find it. And sometimes you can't, like, you have to know that something exists to go there. And how are you going to find something that's good and you don't even know that it exists? Like, so it's like, it's a tricky thing. And I hope that maybe we can also convince our industry partners to release some of their proprietary data into public domain, but I'm not sure if we're going to be able to avoid all the problems that I mentioned before, because like a lot of these data sets and measurements were not made, they were made like, I don't know, years ago, and they were not made with, AI or machines in mind, or how machines might interact with it. And finally, again, more collaborations and data crowdsourcing, because that kind of reduces the cost down. But again, that comes with its own problems because it's complicated and slow. And going back to that life cycle, I mostly was focused on this number 2, performance, and I'm not going to even go into release maintenance and user support. I think that's like probably another hour or a few days of discussing of how to manage that. It's all tricky and difficult. But I think part of the answers to those problems is actually setting up new initiatives and new organizations. Obviously, how we have done things so far is not very effective, doesn't really work. So maybe we need to rethink about it. And I think OMSF is, an attempt to maybe try something new and see if we can, what we can do in this space. And yeah, I don't know, like it's so far, I think it has been promising. We are growing, there's growing interest, and we are learning a lot. And, I don't want to say things are perfect and everything works amazingly, but we are definitely making progress on many levels. And I'm just going to quickly share our org structure. You have we have the board of directors at the top, and then we have projects, and we have our admin. And then these are our projects which have like the lead teams and governing boards, and then we have core teams below. And sometimes we shift people from one thing to another because now we can do it, and we can hire people who do we can hire a fraction of an engineer. And one of the things that we kind of want to experiment going forward is can we also lend a fraction of an engineer to academics? So if you need something developed, or you need to extend, or you want to build on top of what's coming out of OMSF, just let us know or write us into your grant, and we'll give you 25% of our software engineer to, help you set up things, maybe train your PhD student or postdoc. So, we help with building the ecosystem and also save time, right? It takes a long time to get someone new up to date, and how it takes a long time to learn things in general, I guess. And another thing that I guess I wanted to mention, we recently got not recently, it was been at the end of last year, but we got the POSE grant from NSF, which supports pathways to open source ecosystem. They want to see more organizations supporting sustainable open source ecosystem, which is exactly what OMSF is. And one of the goals there is to kind of provide technical support for all of our projects. They all bump into the same issues, for example, Conda Forge packaging. People don't really have experience or don't really know how to do it, if they haven't done it before. So we want to help with such stuff like that. For example, we had issues like missing ways to do CI on GPU. So now the team is developing self-hosted GitHub runners that can be deployed on various HPC infrastructures. We want to create playbooks. So we kind of want to provide guidelines for contributors and collaborators. If you want to join, you should do this. If you want to contribute, you go and behave in this way. If you want to become our project, this is what, also what you need to think about. And finally, streamline administration, come up with the whole legal framework. And because that's you need to think about agreements as programming for people, right? It's if once you put things in place, people will follow it and behave and follow the rules. So if you come up with clean and streamlined agreements, you are doing really well. And yeah, we'll have more deliverables expected later this year. I shared here some resources with different challenges, data sets and stuff. I'm not gonna go into it. You can browse it. I shared my slides, so you can check it all out. But there are some really interesting initiatives in the space and some interesting papers about all of this. And I also was asked to advertise that there are 2 open roles at OMSF. So we hire remotely, and if this is something you're interested in, please do apply. It's for Open Free Energy. We're looking for 2 software engineers. Let us know if you are interested. And I want to say my community manager would be unhappy if I didn't mention that we have a newsletter, so you can find out what's happening and you can subscribe. We send once a month an update about what's going on. So if you want to stay up to date, yeah, just subscribe on our newsletter. We won't spam you. And my slides are also on Zenodo if you want to download it. And I think thank you all for your attention.
We'll have time for 1 or maybe 2 questions. So if you want to raise your hand, I can bring the microphone to you.
Hey there. I was just wondering, do you see at all in the future like the incentive structure in academia changing at all to kind of facilitate this grunt work of coding and doing that kind of stuff a bit more? Or maybe not, maybe.
Yeah. I don't know. I think there are attempts, but it's really hard. Like even with industry, I think it's part of human nature to be more interested in novel stuff. And then you have to find really people who enjoy doing the grunt work. It's not appealing to most people, right? It's creating space for it. And yeah, even when you are aware of it and even when you know that it has to happen, it's still kind of like, against the gradient of interest, I guess, so to speak.